Welcome. In this session in linear data analysis, we'll explore the K-means algorithm for clustering. In clustering, one problem that we always have is how many sets to use. And usually the user gives us a number, and this is usually the number k. And so we need to find a set 1, a set 2, and so on until we found k sets that are partitions. And so let's recall what it means for us to partition. That means that each one of these is a non-empty set, so each one has at least one data vector in it, and it's to be a partition, every data vector has to be in exactly one set. So how can we do this? Well, if we try to do this, so a difficulty is that if we have data that are real numbers with m entries, that this requires on the order of m to the nk plus 1 operations. So this requires many, many more operations than we'd really like. So a heuristic is, instead, we use Lloyd's algorithm. And Lloyd's algorithm is sometimes called the K-means algorithm. That is, when people refer to the K-means algorithm, they almost invariably mean Lloyd's algorithm. And this is quite easy to describe and quite easy to implement, and its complexity is on the order of m for the number of entries in each vector, n because we have to consider every vector, k because we have to consider every one of these clusters, and l for l iterations. And the code for this is in MATLAB. We simply type K-means of our X matrix, and then we have to give it the number K for the number of clusters that we want. So how does this work? Well, let's recall the definition of a cluster. And that is, a cluster is, and these are not mutually exclusive, but we can think of this in two ways. It's a set Si with data vectors, let's call them xj, members, or it could be a centroid, and the kind of centroid we'll explore most is the mean, a centroid, and we'll represent that as the vector gi, and it has neighbors. Let's consider alternating these definitions. And by alternating, I mean, let's suppose that we apply one definition to a set of data, and then we apply another set. So, for example, let's suppose that we initialize the centroids G sub I. And then what we can do with that initialization is, in pseudocode, we can do this. We can say that while we have not converged, we will do this. We will apply this definition first, is that we'll say for each data vector xj, we'll assign index I of the nearest centroid. And then we've applied that, and then we'll apply this, and we'll say, how do we get that centroid? Well, for each index I, we'll compute a new centroid from the points with this index. So how could that work? Well, let's suppose that we're doing binary clustering. So we have a centroid 1 and we have a centroid 2. And then suppose we have a data vector here. So this is the jth data vector that we're looking at. What we do is we take the difference vector between G1 and xj and find its norm. Then we take the difference vector between G2 and xj, find that norm, and then we'll assign xj to either index 1 or index 2, depending on which of these norms is smaller. So in this case, we would take this particular data vector and we would assign it to G1 because its norm is less than the norm of the distance to G2. So why initialize the G sub I? Well, it's fast. And let's make an observation, and this is a general computer science observation, is we could have written this loop so that we begin with this part and then we do that part. And to begin with this part, we would have to have the data initialized. So we could either initialize the centroids and then start our loop by going through the data, or we could initialize our data and start our loop by going through the centroids. That is, in many cases in computer science, when we have a while loop such as this, we can interpret the interior of the while loop. Since it's continually going around and around, we can interpret it as starting wherever is convenient. And in practice, it's fast and easy to initialize these centroids, in particular when we use random numbers. So one challenge that we'll note is the indexes can change between runs. This is a normal situation. Let's also observe that the vector norm matters. That is, there's an infinite number of vector norms, and each norm might have a slightly different behavior on a given data set. So, for example, if we're using the Euclidean norm, which we write as the L2 norm, then we use the mean of the vectors that we're looking at. Another commonly used norm is the L1 norm. This is sometimes referred to as the Manhattan norm or the city block norm. And this norm is when we're taking the norm of a vector, what we do is we take the absolute value of each entry and add up those absolute values. And that turns out to be a norm. And it, on certain data, it has a better behavior than this. And for the L1 norm, what we do is we use the median. And there is often a major difference in the robustness of these between using the mean and using the median. And in both cases, it's whenever we're examining our data vectors. So for other norms, there's ample documentation. There's an infinite number of norms. There are corresponding centroid computations. These are just two of the examples that you can find if you read the MATLAB documentation.